Hello adventurer, welcome to SCARTHQUEST. Today is day 4 of Digital Logic Intake from Z series, and today we will learn about BCD and Gray Code. Let's also understand with BCD. BCD or binary coded decimal is basically conversion of a binary number to a decimal, but it shows the decimal number we see in the screen. What do I mean by that? We all have used calculator in our mobile phone or mobile phone in general. In calculator, we see a bunch of number from 1 to 9 and 0. And we see date, time, or battery percentage in our mobile phone. All these number you see in the screen is due to, you guessed it, B, C, D. So BCD is used for displaying number on the screen. But don't get this confused with binary conversion. BCD and binary conversion may sound similar, but they have whole different concept. For example, a calculator. In calculator, you can see number from 1 to 9 and bunch of plus and minus. The number you see in the screen is due to BCD, but the calculation that happens inside is due to binary conversion. Let's take 2 plus 3. The number you see in here is due to BCD, but the calculation that happens inside is due to binary conversion. So 2 plus 3 and the result. First of all, in computer, the 2 plus 3 is converted into a binary number using binary conversion. So 2 is converted into 0, 0, 1, 0, and 3 is converted into 0, 0, 1, 1, which will give us the result 0, 1, 0, 1, which is 5. So the output or the result we see in the display is due to BCD, but the calculation that happens, the conversion of the number that happens inside, is due to binary conversion. Most people ask me, why don't we use binary conversion both for converting of a number and displaying the number in the screen? Well, let us understand. For example, 23. We need to display the number 23 on the screen. Using BCD, we can easily do that. But in binary conversion, to show the number 23 on the screen, we have to first divide 20 and 3. To do that, we need a separate circuit and more logic gates just to display the number 23, which is very complex. So rather than doing that, we use the BCD. Let us understand how. So the 23 in binary conversion, converting the 23 into binary is basically converting 23 as a whole. So 23 is converted into binary number as whole, which is 1011. So 23 as a whole is 10111. But in BCD, rather than converting 23 as a whole, we convert them separately. So in 23, we convert 2 and 3 separately. This helps to display the number easily and it helps to avoid the error. This is why we use BCD. So in 23, we display 3 as 0010 and 0011. So rather than writing 1011 to display in the screen, we use this number. This helps the computer to distinguish that this is 2 and this is 3. The computer doesn't know this is 23 right away and display it. That's why we use BCD. Hope you understand that. As we have discussed what is BCD, what it does, and why we use it, let us understand how to convert binary number into decimal and decimal number into binary using BCD. Let's start with decimal to binary. Let's take a random number 326. As we have discussed, rather than converting 326 as a whole, we need to convert them separately. So 3 to 6 separately. 3 2 6. If you know the table, which is this, of converting a binary number system into decimal and decimal to convert decimal to binary, it is really easy. This number consists of 10 digits, 0 to 9, and if you can remember, honestly really great. But what if you don't remember the number and don't remember the table? Will you not be able to do this calculation? No. There is easy way to do this rather than remember table. That is the formula of 8 4 2 1. Let us understand how. So what we do is, in 8 4 2 1, we see that how many number add up to get the number in the top. So to get 3, we need to add 2 plus 1. So the number we add, we put 1, and the number we don't add, we put 0. So in here, to get 3, we need to add 2 and 1. We don't need 8 and 4, so we put 0 and 0 in there. In 2, we again use 8 4 2 1. Here again 2 is already there, so we put 1 in here. 8 4 and 1, we haven't used it, so we put 0 in there. Now comes the turn of 6. Again we use 8 4 2 1. We see which is number give us the top number. Here that is 4 and 2. It doesn't give us any, we don't use 8, so we put 0 in here. We use 4 and 2, so we put 1 and 1. We don't use 1, so we put 0. So we get 0 1 1 0 for the 6. If you see the table, you can see that this is the right answer. So the total value of 3 to 126 in BCD is 0 0 1 1 and 0 0 1 0 0 1 1. Yeah, this is a very simple way of converting a decimal number system into binary. Let's take another number, 4 to 6. Let's go much further, 8. In 4 to 8, we again use the formula 8 4 2 1. Here we can already get 4, so we put 1, other 0. To get 2, we again use 8 4 2 1. Again there is already that, so 0 0 1 0. In 8 8 4 2 1, again there is 8, so we use 1 and get the answer. So the answer of 4 to 8 in decimal in binary is 0 1 0 0 0 0 1 0 1 0 0 0. Using this 8 4 2 1 formula, we can easily find the BCD of any number without remembering the table. Now let me give you a fun fact about using this table. So people ask me a lot that why don't we use hexadecimal and other number system for in our screen and stuff like that. Here you can see that we have 9 digits in our decimal number system. This is the number system we used in our daily life. You cannot find number beyond this. You add 10 plus 1, all the number you can find from 0 to 9 in here. Imagine finding a time for line 4a. How could you decode 9 4 as time? You see 10:30, 10:50 and say, oh, it is midnight, it is morning. But saying 9 4a, 9 4b, it is confusing. So we use decimal number system rather than other number system because we human understand the decimal number system better. And another fun fact, we use BCD binary number system because there is 9 digits, and in BCD we only use single digits, as we rather than converting a number in as whole, we convert them separately. This is also reason why we use decimal. This is one of the fun fact or reason most people are confused with. I hope you understand that too. This is a very short summary or uh, of BCD and what BCD is. If you want to know what more about BCD, there you can search in YouTube. There is much more video which tells you what BCD does and what BCD is about. I hope I made you understand what BCD is. Uh, so yeah, let's go to the Gray code now. Now let's learn about Gray code. Gray code is basically a code that is used in devices which relies on precise, continuous measurement of the position and the value. The value changes from time to time and needs accurate result of the movement so that there is no transition error. It does that by only changing its value by 1 bit. So the gray code is a code that is used in devices whose value changes from time to time, and we need the continuous, precise value of the position change, and that is done using gray code. Some devices that uses the gray code are rotary encoders such as mouse wheels. Not entire mouse uses the gray code, but just the wheel of the mouse. And other devices are analog devices, ADC, and sensors like motor sensors, dials, and much more. All these devices I have just mentioned have one thing in common, that is, their position changes from time to time, and we need the accurate result of their position. Gray code is used for that. Gray code looks similar to binary code, but unlike the binary where the value changes by one or more than 1 bit, in binary code the value changes by only 1 bit. Let's see how does it changes by 1 bit. So in binary, as we have read the table, it goes from 000 to 0001. Up to here there is nothing wrong. But after this, as you can see here, the 001 becomes 0010. At first, it doesn't look that big. But here, the 0 has become 1 and 1 has become 0. And after 0011, the value have become 0100. Here, the value have changed by 2 bit and more. But unlike the binary where the value have changed by 2 or more bit, in gray code the value changes by only 1 bit. So in up to here it is same for both binary and gray code 001. But after 001, in binary the value has changed from 001 to 0010. The 0 have become 1 and 1 have become 0, making the 2-bit change. But in gray code, rather than changing the 1 into 0 and 0 into 1, so it becomes 10 and there is 2-bit change, we keep 1 as it is and just change the value of 0 to the 1. Rather than directly turning the 01 to 10 or 10, we first turn the 0 into 1, only then we turn it into 10 by converting the last 1 into 0. After that, we convert the first 0 into 1 so that we get the value 100. Only after we turn into 0, 1, 1, 0, we make it 0, 1, 0, 0 or 100 by turning the 1 into 0. So what we are doing is we are changing the value of 1. We are skipping some of the part and we are just we are making sure that the value changes by only 1 bit. But why does it even matter? Why does changing the value by only 1 bit what does it even matter? Well, let's take mouse wheel for example. In the mouse wheel, there is like a thin color ring. Each time we scroll using the wheel, the ring value changes by 1 bit, or the value changes by 1. If you use the binary code instead of gray code, let's say I'm scrolling through reels. While scrolling, I want to go from reel 1 to reel 2. To do that, I scroll it one time. So the ring value changes from 1 to 2. Here using the binary value where 0001, which was the first value of the when I was entering 1, to 0010, the value of 0010, there is 2-bit change. Computer get confused after seeing the 2-bit change. Rather than taking us to reel 2, which was our desired position or desired place, it takes us to reel 3. Let's see how. Let's see how does it causes the error. Now let's learn how transition error really occur when using binary in devices where constant measurement is needed. First of all, we must understand that binary code is more used or more commonly used in situations where distinct states are essential, such as CPU processor or memory, rather than the continuous measurement of the data. So in a circuit, there is when data is read, for example 0001, it is not read in sync. So it is not read like 1000 in sync. It is read at a random or rapid space. So in a situation where we need to give feedback at a rapid space continuously, this is the main key, continuously. So what happens when we use binary is that, as we have said, the bit changes by 2-bit. So bit have changes by 2-bit at a continuous rate. As we have sending the data, it can cause error by reading. What can happen is, after 001, rather than reading 0 and 1 as it is rapidly continuously reading, it can skip the 1 and make it 000, causing the transition error. So in binary, what happens is, as it is binary is made more for a distinct state, so a jump, rather than a continuous feedback, continuous change in measurement. That's why binary is not used. So rather than binary, gray code is used. In the gray code, the value changes by 1 bit, and computer understand that. So what happens is 0000 becomes 0001 and 0011. There is only 1 bit change, as it is sending the value as in a devices where continuous measurement is needed. There is only 1 bit change, so there is no error, there is no jump. So 001 0011, so there is really no jump, it is changing by 1 bit. Hence, that's why we use the gray code in devices where value or changes from time to time. Fun fact, in a mouse wheel, as it uses the gray code, it is still converted back to binary. So the gray code we use in the mouse wheel is converted to the binary to give it to the computer, as computer doesn't understand gray code. But how do we even use, why do we even use the gray code if we have to convert back to binary? Well, remember this very fundamental, the very principle of gray code. Gray code is used to track and give the accurate result. It's used for accuracy, not for the speed. As we have said, it needs a continuous measurement of the data, but not just any continuous measurement. Binary can read the measurement, but not accurately. Gray code is used for that, not for the speed, but for the accuracy. So we can convert the gray code to binary and binary to gray code. Let's learn how computer convert the gray code and gray code to binary and binary to gray code. Let's start with binary to gray code. We can convert the binary to gray code in a very simple manner. Let's take a random binary like this 110110. Let's convert it into a gray code. What computer does it? Let's see. Computer basically uses XOR gate or other stuff to uh, convert the binary into gray code. In a mouse wheel, a XOR gate or any other gate is located inside the mouse, so it converts the gray code into a binary. First of all, let's understand how to convert a binary to a gray code. When converting, what we do is first of all isolate the first number. Have you done that? Then bring down the first number down. That's it. You don't have to do anything. Just bring down the first number at first. That's the first thing you must do. Whatever you are converting, whatever number you are converting to gray code, whatever binary code you are converting to gray code, you must first bring down the one down. Then it is the magic start after that. What we do is, after bring down the first number, we compare the left number with the right number, left number with the right number. And if the left number and right number are similar, we make it 0. And if right number and left number and right number are not similar, we make it 1. So let's compare 1 and 1. As 1 and 1 is similar, we make it what? 0. After we compare the right and left, we again compare the right and the left. So 0 and what is again, it is in left, so in left it is 1. So 1 and 0, as it is different, we write it 1. Then 1 and 0, again we compare the right number with the left number of, so 1 and 0, as it is different, we write it 1. 1 and 1, as it is same, so we write it 0. 0 and 1 is different, so we write it 1. So let's do other number 2. 1 0 1 1 1 or 1 0 0 0 1. As we have said, first bring down the first number. As there is no number at front, we just bring down the one number, as we cannot compare it to other number. That's the thing. So after that, we compare the right number with the left number. So 0 and 1 is different, so we make it 1. 1 and 0 is different, so we make it 1. 1 and 1 is same, so 0. 1 and 1 is same, so 0. 1 and 1 is same, so 0. 1 and 0 is different, so 1. 0 and 0 is same, so 1. 0 0 is again same, so 1. 0 is same, so 0. 0 and 1 is different, so 1. So what we have to do is bring down the 1 as it is, then compare the number left right to the left. If left and right are the same, we make the number 0, and if they are not the same, we write them as 1. That's the main principle. That's how we can convert, or us human can convert the gray code, the binary code to gray code. In computer does it really fastly, but if you have to understand how computer really does it, this is the way to so in summary, when converting a binary number into gray code, bring down the first number as it is, then compare the right number with the left number. If the right number and left number are same, we write it as 0. And if they are not same, we write it 1. I hope you understand. In our next video, we'll be discussing how to do it further. So this much is the basic. Now let's do another, that is gray code to the binary, which is done inside the wheel of the mouse. So let's take a random number. Let's say this is a gray code. Let's convert this into the binary. Previously what we did was we bring down the number as it is and compare the left number with the right number, and so that if they are same, we make it 0. If they are different, we make it 1. Well, it is same in here, but the way we do it is very different. We bring down the 1 as it is. Rather than comparing the top number 0 and 1, now we compare the bottom number and the top number. Previously we just compare what was in top. So if it was 0 1, we compared 0 1. If it was 1 1, we compare 1 1. We never look at the bottom number. But in the conversion of gray code to the binary, we now compare the bottom number to the top number. So 1 as it is, we compare the the number we get as the bottom to the top number, just side of the number we are finding. So 1 is compared with 0. 1 and 0 is different, so we write this. The answer comes down as 1. Again, we compare the bottom number with the top number, the number we are trying to get. So 1 and 1 is same, so it becomes 0. 0 and 1 is different, so it becomes 1. 1 and 1 is same, so it becomes 0. So the principle is bring down the number as it is, then compare the number next to the number we have just found. So as we have just found 1, we compare the number next to it with the result of the number we have found. The result of the number we have found is 1. Now we compare it to the number right next to it. So 1 is compared with the number right next to it. If it was 0, 1 and 0 is compared. Then we just bring down the result right below it. So 1 compared to 0 is 1 as it is different. Let's say if it was 1 in here. Now again compare the bottom number with the top. As it is same, we make it 0. This is the core principle. I hope you understand. In computer it is again done fast, but we do this and to understand how computer really understand and does the conversion. Let's practice some numbers. 1 0 1 1 1. Let's try a different number. 1 1 0 0 1 1 0 1 0 1. Let's convert the gray code to binary and binary to gray code. Okay. When converting a gray code to a binary, first of all, whatever it is, bring down the 1 as it is. As previous, there is no number, so this is the answer. 1 is compared with the top number, which is 1, which will give us the result 0. 0 and 0 is same, so again 0. 0 is 0 is same, so again 0. 0 and 1 is different, so 1. 1 and 1 is same, so 0. 0 and 0 is same, so 1. 1 and 1 is same, so 0. 0 and 0 is same, so 1. 0 and 0 is same, so 0. 0 and 0 and 1 is different, so 1. Let's do this again for confirmation. 1 1 0 0 0 0 1 1 0 1 0 1. It is like the crisscross. 1 as it is, 1 is compared with the 1 to get 0 as it is same. 0 is 0 is same, so 0. 0 and 0 is same, so again 0. 0 and 1 is different, so 1. 1 and 1 is same, so 0. 0 and 0 is same, so 0. 0 and 1 is different, so 1. 1 and 0 is different, so 1. And 1 and 1 is same, so 0, which gives us a different result. Now let's convert this back to the binary. So 1 0, what we get was 1 0 0 1 0 0 0 1 1 0. Now let's convert back to binary to gray code to see if my answer was correct. Now this is different from gray code to binary. As I said, we just bring down the 1 as it is. Then rather than comparing the top bottom number to it, top we convert the side, so 1 and 0 is different, so 1. 0 and 0 is same, so 0. 0 and 0 is different, so again 0. Sorry, same. 0 and 1 is different, so 1. 1 and 0 is different, so 1. 0 and 0 is same, so 0. 0 and 0 is same again, so 0. 1 and 1 is 1 and 1 is sorry, I done the mistake. Okay, sorry, it happens sometimes. So first of all, let's compare 1 and 0. 1 and 1 becomes 1. 1 and 0 will give us 1. 0 and 0 will give us 0 and 0 will give us 1. Sorry, 0. 0 and 0 will give us again 0. 1 and 0 will give us 1. 0 and 1 will give us again 1. 0 and 0 will give us 0 and 0 will give us 0. 0 and 0 again will give us 0. 1 and 0 will give us 1. 1 and 1 will give us 0. 0 and 1 will give us 1. Is my answer correct? 1 1 0 0 1 1 0 0 1 0 1. Yes, my answer was correct. So I hope you understand what is a gray code, what it does, and how to convert a gray code to the binary. That's it for today. For summary, I will tell you that a gray code is used in devices where a constant measurement is needed. We use gray code instead of binary because binary can cause transition error and gray code avoids transition error. So we use the gray code, and most devices convert gray code to the binary, sometimes binary to gray code in ADC devices. And we learned about how to convert a gray code to binary and binary to gray code. There is two different ways of doing that. I hope you understand how to do this. I will meet you in the next video. Bye bye. Tada.